Thank you, Scott. Today's speaker is someone who has been with us in terms of doing energy audits and has done quite a good job. Dan Schruaben, he has a degree in civil engineering. He is also a professional engineer, and not only has he been doing ag energy audits, but also has been experienced in the industrial side of energy audits. So without further ado, I turn it over to Dan.
Thank you. Good morning, everyone here. Hear me okay?
Yep.
Okay. Yeah, so again, we're part of the Ag Energy Professional Development Series. The topic today is milk cooling, water heating, and heat recovery. As Al mentioned, I am a engineer, licensed engineer, but also a certified farm energy auditor through the MSU program. And a very interesting, I guess, evolution for me. My background is over 35 years of consulting engineering in the private sector, working with municipal wastewater systems, water systems, private development projects. In fact, I guess the last project that I was on was a large shopping center. And over a period of a couple of years, to my knowledge, that shopping center has one major store in it because the economy kind of stopped it. But it also was about time for me to move on anyway, and basically the wife said, well, you've cleaned out the garage, go find something else to do. So I had the opportunity to enroll in the Farm MSU Training Workshop back in 2009, and it's been a very good education from the technical standpoint. Certainly you need that information, and I was able to grab that, but I think the other part is some of the practical aspects of it when you're actually getting on the farm and try to understand the farm operation and whether or not this particular energy efficiency opportunity is something that's going to work with them and affect their operation. So the milk cooling, the water heating, heat recovery, here's just an overview of the topics that I'm going to run through here today for you. The energy usage, milk temperatures, milk cooling equipment, the pre-coolers, plate coolers, and then the opportunity to reuse that plate cooler water, a little bit about the EQIP program that's helping offer an incentive for that, and then other components of the system, just highlight the bulk tanks, compressors, condensers, evaporators, and then we'll talk more about water heating and the preheating and heat recovery opportunities with that. Just some basic information, and certainly you've seen these values or aware of these numbers, the energy conversions. I think the important thing that I've learned or I've seen in using these, that there can be a variety of values, and the key to it is be consistent. I've seen liquid propane values as high as 96,000 and as low as 89,000, and I think the key is just be consistent when using these conversions so that you are comparing the energy option or opportunity with the existing condition, and it's a representative value. Just another thing to be aware of with the energy efficiencies, again, you got the energy potential that's listed in the second column there. That certainly is a value that's the capability of that particular energy source. But as it's being utilized by the equipment or the machinery or the particular operation, then the efficiency of that equipment enters into play. And so you can see, obviously, the diesel and the gasoline with the engine efficiencies there drop off quite dramatically. So the net energy produced through that is going to be something less. Again, something just to be aware of as you're considering these various energy operations. And I think my whole approach, or what I've seen too, has been more of a practical approach as opposed to a theoretical approach. I mean, I've got a basic understanding of these systems, but I think the key is to be able to identify them in the field and try to understand what the operator is trying to do. Or they're all trying to put milk in the tank. They all have a little different way of doing it. So the key is to listen to them and see what may work for their particular situation. Even though the numbers may look good from an energy standpoint or an energy efficiency opportunity, it may not fit into their operation. Here's information that Michigan State provided me for Michigan. It's fairly current data, as you can see. The various sources or energy users relative to a dairy farm system. I think the thing that you need to be aware of are these the two blue areas where you definitely have a little more energy usage, as you can see. And here again, here's that same list given, but you can see the two top ones for the Michigan area are the milk cooling and the water heating. So it certainly is a significant energy user, and I guess you could look at it as an opportunity too, that hopefully there's something that can be done there to help minimize the energy use for those particular operations. Other states, here's some older data from both Wisconsin and New York, and you can see the similar values for the milk cooling and water heating in both of those aspects for New York and for Wisconsin. There's perhaps more current data, maybe with some of the energy efficiencies being put into place, perhaps that's changing over time. But again, it's a significant portion of the energy usage for the dairy operation. Again, Michigan, again, a large part, so we're going to focus on the milk cooling. It's 18% of that energy use, and then get in and discuss water heating for the other significant portion. Just some basic terms, and perhaps most people understand this or are aware of this, but the BTU is the heat required to change the temperature of a pound of water 1 degree. So those are the terms that we're going to be dealing with here. Just as to give a reference for numbers, so a cow that's 35 pounds per milking 2 times a day is 70 pounds a day. We're looking at 4,200 BTUs per dairy cow, a significant amount of energy. If you even take that further, with a 200 milking cow herd at that 70 pound per day average, you're coming up with over 300 MMBTUs per year, and that's equivalent to more than the energy used for 10 homes. So again, a significant amount of energy, and it's certainly a reason why we're having these types of discussions, and there's more focus on this to try to do something better in that regard that both saves energy but hopefully helps with the farm operation itself and increases productivity. You've seen the basic diagram for the various components. It's probably been discussed before or presented. But what we're going to focus on is the right hand, the area that's shaded in the yellow color. We're going to talk about the plate cooler after the milk pump as it goes into the milk tank, the water, the well water, and the discharge water from the plate cooler into the cooling system, condenser, and into the water heater and the preheater opportunity as we move through the discussion here today. Something to keep in mind, and this is pretty well acknowledged, that the plate cooler or pre-cooler is one of the best energy investments. It's an inline pre-cooler. It's prior to the bulk tank. As you can see on the diagram here, here's your basic components, and the plate cooler or pre-cooler connects at that point in the system. Plate cooler is a relatively simple piece of equipment. It's just a series of pipes and plates. And the water and the milk are channeled through that. Wall-mounted, floor-mounted, sizes vary, but depending on the milk production or the needs, that can determine that. In fact, this particular one here is actually set up to be expanded if they expand the operation to add a unit to it. Okay, the purpose or what the plate cooler accomplishes, it's able to cool that milk 20 to 40 degrees, and it's done by the water running adjacent to the milk. It's not in contact with the milk, and you're looking at 45 to 55 degree well water temperature to grab that heat, if you will, and the net result is it reduces the runtime of the condensing unit that is a more significant energy user in the milk cooling operation. Various kinds or terms that you need to be aware of with plate coolers: single pass, dual pass, two-stage. But as you'd indicate, or it implies that the more passes through the plate cooler, perhaps you're going to get more temperature reduction. But this is dependent on, the coolant flow rate itself and the number of plates. So the configuration of the plate cooler dictates that temperature loss or of the milk. Again, a delta, we're looking at 100-degree milk, and it needs to be cooled within 2 hours down to 40-degree temperature. So there's, again, a significant amount of energy that must be used in order to achieve that and assure the quality or maintain the quality of the milk. Okay, groundwater in Michigan is about 45 degrees. So this is the vehicle that we're using to cool the milk. And other areas of the country, this varies, and obviously further south you go, you're going to get a little higher temperature. But in Michigan, we're comfortable assuming or using the value of 45 to 50 degrees. Again, just numbers again, but it's the cooling capacity of well water, and so about 440 BTUs per gallon is what it can accomplish. Again, the plate cooler, its effectiveness is dependent somewhat on the flow rate through the unit. The key is to have the most continuous flow rate you can to optimize the contact time between for the milk that's running adjacent to it and the well water that's providing the cooling. Maintenance, again, a relatively simple machine, but here's some, I guess, operational problems that I've heard about or am aware of in working with the various farms that I've been doing audits on. In fact, two farms actually had, there was no way they were going to put in a plate cooler. They had too many problems with it, with mineral deposits clogging up on them, and it was becoming a maintenance issue for them. And they just had enough things to deal with their dairy operation. They did not want to have that to deal with. So it is something. It could be something in the case of Michigan where that is an issue. In fact, I'm aware of one farm in Michigan that actually is their well water source has brine in it, so they're having to use collected storm water for their plate cooler cooling. So the capacity of the well, or that could also be an issue. An interesting thing here on the one farm that just said there's no way he's going to have a plate cooler. We did the energy audit. Once he saw the numbers, it's my understanding that, in fact, he has a plate cooler now once he saw the value of it. And I guess that's part of the purpose of the audit. It's not necessarily a mandate to the farm. It's an idea or maybe a priority list of items that they could consider and implement if, in fact, they want to move forward here and help improve their operation. The other simple, I guess relatively simple things are just, we're seeing this more on the plate coolers. They're seeing just strip thermometers that are on the outlet pipe so they can monitor it more closely that it's doing its job, or they've installed temperature probes, or they're monitoring more closely the temperature as it enters the milk tank. And even another case, one was actually monitoring their condensing unit time, and if any of those fell out of line from what they felt they should be doing, then that was an indication they needed to check something out or do something. And there are chemicals or means to take care of the periodic flushing. So there's I guess systems out there to help deal with that. So it's a manageable situation from a farming operation standpoint. Just as a kind of a reference point here, it's the energy utilization index that's sometimes used to reference for energy improvements. So conventional cooling is, call it the baseline, if you will, so 0.8 to 1.2. With a well water pre-cooler, then you're able to get that down by a factor of 40% here, which is pretty significant. I think that one point to mention, the pre-cooler with the milk pump VFD, the importance of that, or the reason you're able to achieve better energy efficiencies in that particular situation, is the VFD will stabilize the flow and make it a more constant flow through the plate cooler, and with that, the flow is matching the flow of the water more closely, and you're affecting a better temperature reduction. So that's an important component if in fact that is installed along with the plate cooler. The plate cooler water flow rate to the milk flow, it varies based on the manufacturer's specifications. And again, as I mentioned, it may even be a factor of just the capability of the well to produce the water. The literature is indicating a variety of values from 1.1 to 3.1. So it's, but what we're seeing in the field and based on some observations and even in situations where they are collecting the water, if you will, for water reuse, we're seeing closer to 1.5 to 1. This seems to be more typical, and in part that may be that the technology of the more current plate coolers is doing a better job to utilize that water and cool the milk. The Michigan dairy suppliers that we are in contact with, they're recommending a 1.25 to 1. So that seems to be the value that's working in the Michigan area, but again, it could vary, and other values may be appropriate. Yes, and just to understand or try to quantify the amount of water that would be the result of using a plate cooler, if we use the 1.5 gallons per gallon of milk cooled, 70-pound per day average milk cows, 8 pounds a gallon, and then we're looking at an average of about 13 gallons per day per milking cow. So if we take let's say the more typical farms that we're seeing in Michigan, the 100 to 200 head, and then we look at that as close to 2,000 gallons a day of water that we're going to use or need for the plate cooler to function. Okay, the question then is, what do we do with that water? We just discharge it to waste, or we try to reuse it? One particular farm that was actually discharging it to waste, they were debating whether they should reuse it or not, and we said, well, what's happening with the waste? In their particular situation, the manure lagoons were actually near capacity, and they were quite concerned about that, of course. And then we just said, well, here's the kind of value you're looking at. 2,000 gallons a day, it's over 700,000 gallons a year. And they were contracting with a land application applier at $0.015 a gallon, a pretty significant cost for treating water that hadn't been contaminated prior to its discharge into the lagoon. So that opened their eyes and said maybe there's something else we should take a look at or consider. And so the discharge to waste or reuse question is viable, and that even the cost of land application may be a consideration. Certainly the land applications, especially in many states, are becoming a little more stringent. I think there's more awareness of that, and I think that's a factor that can come into play. And again, this particular farm operation, they actually were limiting their plate cooler flow in order to reduce the discharge to the manure lagoons, and as a result, they weren't seeing as the best results from their plate cooler. The effectiveness was being reduced. I think it's fairly well documented that the livestock prefers the warm drinking water. They will drink more water if it is warmed. In fact, on one farm I was at, he said they actually prefer the warmed water even in the summer months over just the well water for drinking. And then related to that is the milk production increase with more water intake. And then the added carrot that we have here is USDA is encouraging water reuse through an incentive payment program. And here's just the various parts of USDA that are involved, the NRCS, and then the EQIP program, agricultural water. Their water quality incentives is how the program is viewed and set up. And currently, right now, it's a one-time incentive payment of about $2,900 for 2011. Okay, if in fact you have the plate cooler water, then how does that relate to the drinking water demand? Certainly, or the plate cooler water is accumulated during the milking cycle, so that's only 2 to 4 hours a day, a couple times a day. But the water demand is 24 hours a day. There's significant demand, but that's also dependent on the particular animal that needs the water. So again, we try to quantify that for the operator, and then they can make a decision how best to handle that. So the water demand, so for 150 milking cows at 40 gallons is about 6,000 gallons a day. The plate cooler, as we discussed earlier, it's about 2,000 gallons a day. So there's certainly more demand than there is water generated, but it's a question of how can we get that water to that so it can be utilized as drinking water. So some of the things that we're aware of, it's indicated that 30 to 50% of the water intake actually occurs right after milking. So that would make sense that that's an area to consider to provide the watering system. And then whether it's in the holding area, freestall barn, or other areas, and again, which animals need the water would dictate how much water they can be provided and utilized. And what EQIP requires is they want 100% reuse, so they want an approved plan. So with these numbers, the farmer operator is able to come up with a way to utilize this water to assure that he's got 100% reuse. Typically, what we're seeing is just some type of water storage tank and pump. More often than not, some distribution piping and watering tanks, of course, are in place. So it's a matter of holding that water for a while and then directing it to an area that can use the water when it's needed. So the typical cost range for just this simple setup is less than $1,000, and EQIP at the $2,900 payment more than offsets that and allows even some time for money to put some additional tanks in, if watering tanks even, or distribution piping. So it's certainly a good incentive program, and we're seeing the Michigan farms certainly trying to take advantage of that. Another little side benefit, plate cooler water, since it is warmed, and there's active livestock usage with the waterers, even the waterers that they're using, it's minimized or eliminated sometimes the need for heaters. So it's kind of a secondary energy saving benefit that's occurring by using the plate cooler water. Here's just a couple examples of tanks that were set up. Both of these were just outside the milking parlor, but again, a simple piping set up in order to direct the water to the tanks to the areas that the cows could access it, and it was working well for them. Okay, another component here, milk tanks. Certainly probably familiar with these, but they come in various sizes and configurations depending on the operation. Some are through the wall or outside partially or totally enclosed, but it's a component of the milk cooling operation. Relatively simple device. The components of it that use any energy, the inspection light and agitator motor, are minimal energy usage, so there's not much to consider there. Where the work gets done is in the interior with the interior cooling system. And there's two types of basic systems, direct expansion and instant cooling. The direct expansion usually occurs within the bulk tank, or it does occur within the bulk tank, and it's related to the evaporator plates that are basically capturing the heat. Instant cooling is external to the bulk storage tank. It's more commonly used in larger farms. I have not actually seen this type of system yet, and it's my understanding that even in some larger operations they're actually bypassing the bulk tank and directly to the truck by using the instant cooling process. The refrigeration cycle, again, without getting into a lot of detail or a lot of understanding of how it actually works, I think it's just to be aware of the major components, the condenser, the compressor, and the evaporator that are the elements of this system. The compressor, as it's named, it compresses the refrigerant gas. The evaporators absorb the heat from the milk, and then the condensers are transferring that heat, usually to water or air, in order to dissipate it. Condensing unit, you'll hear this term, so it's comprised of the compressor, the condenser, and its controls is what's comprised of compressor or a condensing unit. Here's a catalog cut of the one that's actually installed in a dairy operation, and it's interesting. This is a relatively small operation, but this has been operating for their only unit, been operating for years and doing the job. So they're pretty durable pieces of equipment and certainly necessary for the particular operation. The compressors, again, just more be familiar with the terms. These are terms you quite common or might be aware of, hermetically sealed or accessible hermetic. But what is becoming more dominant in the that we're seeing in the field as these compressors age or they need new equipment, the scroll compressors are becoming more dominant, and for the right reasons. They have a higher efficiency rating, lower noise levels, reduced vibration, shorter runtime. So for all the right reasons, this is becoming the dominant one that we're seeing in the field. Again, condensers, air-cooled, water-cooled. Again, we're seeing both kinds. Water is a better carrier of heat than air, but it's not uncommon to see just the air-cooled condensers as well. Okay, for water heating, what we're seeing in the field is just the conventional water heaters. They can be either commercial or residential grade models. And these typically have a rating of about 80% efficiency new, but we're seeing once they're in the field and if they're an older model that because of their age and their conditions that the efficiencies have dropped off, and we don't think it's unreasonable to assume a condition as low as 70%. Okay, so what are the options for water heating? What can we do? What are the energy conservation measures that we can consider? Well, certainly higher efficiency water heaters are available now, so that's a possibility. We've seen in a couple situations actual and on-demand water heaters are being used. So it's a product that's certainly been developed here to the point where it's, I think, an acceptable option here for even a dairy operation. And some basic stuff, just piping insulation and blanket wraps, certainly can be still utilized. And then is there an opportunity, or can we preheat the water or use the heat from the milk cooling system in order to enhance the water temperature and put less work on the water heater. Michigan State University has made available to us an online calculator. There's some it's information that they've developed and are confident in its usage. So we're able to make ourselves available of that tool. But for water heating, here's specific information that we need in order to do that. Just the hot water usage, of course, and then the hot water heater specifications in order to establish a baseline. So the quantity of heated water, the temperature set point, a minimum of 165 degrees is needed for sanitation purposes, but it's not unusual to learn that the operator might be using a set point as high as 185. So that's information that's needed in order to calculate its energy usage. The inlet temperature, assumed value of, say, in the neighborhood of 50 degrees, well water is the source. Ambient temperature is the temperature of the area where the equipment's located. Certainly that varies over the year. It's certainly higher in the warmer months and colder in the summer months, but we find that a value of 60 degrees is a reasonable assumption for the ambient temperature that we need in our calculations. Again, the data comes right off the nameplate of the water heater, so we're looking for the rated input capacity, and the important item is the model number. So with that, we're able to come up with a standby heat loss coefficient. So this is the energy used while the water heater is truly just standing by, just to maintain that level of temperature. So with the brand and model number, we're able to go to the AHRI site, air conditioning, heating, and refrigeration, and when they have a certification process for the equipment, and then by using that data, we're able to get the recovery efficiency and their standby loss for that particular unit, and then we're able to calculate the standby loss coefficient that's used with the MSU calculator. And there you can see the set point temperature and the ambient temperature where they come into play. The other challenge we have, though, is some farming operations are able to use a residential grade water heater, and AHRI does not have the standby loss for them. So we're able to go to the table, get the energy factor, and then with the recovery efficiency and the input power, we're able to calculate using the formula here of the actual standby loss coefficient, again, to use as a value for the online calculator. And then here's their website for that. We basically insert the information, and then the result gives us a BTU per day for that particular water heating unit. And here's an example of where we actually compared the existing water heater that was about a 75% efficiency to a higher efficiency unit that was probably closer in the neighborhood of 95%. And then we were able to get the usage in BTU per day for each of those units. And as you can see in the third column over, the difference in BTU over the existing over the proposed. And then that's extended out. We're seeing the energy differences. We're seeing the LP gallons used in this particular case. The cost is about $2.40 a gallon. And then we're able to go down here and look at compare those and look at the savings. Almost $600 in just LP cost. Here's the replacement cost, and able to get a payback. This is a reasonable payback. We generally like to look for something 5 years or less. But if, in fact, this energy audit is the basis for a USDA REAP, Rural Energy for America grant, this 4 years to 8 years is also a category that has a reasonable point value in the scoring system for the REAP application. So in this particular case, even at 5.8 years, this would be a recommendation to change it out and install the newer unit. Here's just an example of a higher efficiency unit. Again, they're out there. They've been on the market. They've got a track record. So it's something that can function in a dairy farm environment. Here's one where we came across for my first experience with an on-demand water heater. It was a particular dairy farm where the existing water heater failed, and they actually had just recently installed an on-demand unit. So, and even the question with that, and that was a concern they had too, was whether or not it can meet the relatively high demand during the milking cycle. And it was working. This particular unit was capable of 3 GPM for 135 degree raise in temperature, and it said they did indicate it was working adequately for them. So what we did is we took the old water heater and just compared and just looked at the value of that unit and the BTU per day, and then we're able to look at the savings down here again. It was a reasonable savings. The unit is about $2,000, a little longer year payback. I guess the point was, I think they even made the point, well, when we put the existing water heater in, we didn't have a payback on that, so maybe 9.4 years isn't unreasonable. So kind of an interesting comment, I thought. On demand, just another term just to be aware of, is tankless, and that is the reason. It does not have a tank. It's instantly providing the water at the temperature needed, hopefully at the demand rate that they need it for. Here's another calculation that we're doing. It makes sense that the piping is exposed and it's in an environment cooler than the temperature of the water, that you're going to have basic heat losses based on pipe loss calculations. So again, the MSU calculator is a tool that's available to us. This particular farm is a relatively small operation using less than 200 gallons a day. I only had 25 feet of pipe, but yet there was a significant or a worthwhile payback for him just to do the simple pipe installation for his system. Another opportunity or another thing is the blanket wraps. Again, we're looking at minimizing the hot water temperature losses in the open air environment. As long as there's not a moisture environment, some of these utility rooms may accumulate moisture, and that could be a problem. But if the opportunity presents itself as something that's a simple, easy thing in order to preserve some of the temperature for the heated water. Generally, we're seeing the equipment waste heat in utility rooms for milk operations. I mean, that heat is used. It's used, serves as a source of heat for the utility room, even the milk house or parlors. It can be vented to other areas. Certainly during summer months when it's really warm, then it's got to be, vented to the outside, and there's exhaust fans that are required in order, and their energy are required to do that. The furnace that you see in the picture here is probably more typical of what we see, the type of furnace or unit heater that's there because of the minimal use. And it's probably not the best looking, I guess, piece of equipment, but for what their needs are, it works. But even with that, so you've got that waste heat. Is there another area or something else you can use that for, and is there an opportunity to use that to preheat the hot water? As I mentioned, the equipment rooms vary. I mean, most of them are certainly, for the right reasons, are fairly neat and tidy operations, but every once in a while, this one I came across in the lower right here, pretty much packed utility room, an older farm that had evolved over time, and truthfully the space was somewhat cramped. So do they have room to even consider adding some equipment or some more machinery in order to accomplish some energy savings? So the practical aspects maybe come into play again sometimes when we talk about these energy efficiency opportunities. What are some of the preheater options? Well, in addition to heat recovery units, we're actually seeing some biomass boilers utilized in Michigan farms. It certainly seems to make sense. They're either using wood or wood pellets or corn, although I know the ones that are using corn, because of the price of corn, they're moving away from that, and wood or wood pellets seems to be the fuel of choice for the biomass boilers in this particular setting. And you can just see it see it here as an example of just a preheated storage tank next to the water heater that this particular unit was preheating. In this case, though, the wood heat was actually being used for the residents, and they just thought, well, why not? Why not preheat the water for the dairy operation? So their heating season, they're only using it part of the year, and so we tried to evaluate that and take a look at what that meant to them. So we looked at the case of where it's preheated, and you can see a significant lower BTUs per day. And then even though it's 240 days use compared to the 125 with no use, there was a significant savings of over $500 a year for that particular operation. So it was a value to them to do that, and it was done kind of as an aside when they were connecting their heating system or upgrading their parlor. The other option for heat recovery is the actual preheat hot water, or preheat hot water is the heat recovery units. Mueller, Thermistor are a couple brand names that we see in the field, but essentially they're capturing the heat from the condensing units, and they're capable of preheating the water typically in the range to 120 degrees. So it's 70 degrees over the well water temperature of 50 degrees. And certainly that would indicate that the water heater has less work to do in order to get that up to the set point of 165 to 185. Here's an example of that same on-demand unit where we looked at the possibility of adding a preheater unit to that system. Again, when you look at the values, so here's the on-demand or BTUs per day for that on-demand unit, pretty significant, but with a preheater it almost cuts that in half. And again, pretty significant savings. We're looking at just at LP at $1.50 or about $1,000 a year, and with the installed cost of the preheater about $3,000, that made a pretty easy decision to think that ought to be something to be installed. One thing to note with that, though, in this particular on-demand heater, this is the one where they were concerned about its demand capability, and because you have a lower temperature rise of 65 degrees, you've actually doubled the GPM capability from, if you remember previously, we talked about 3 GPM by using a lower temperature rise. Again, almost double the capability, or did double the capability of that, and that better assured them that it was going to meet the demand that they needed for their particular operation. So an on-demand in conjunction with a preheater may be a viable option for a dairy operation based on this scenario. Something to keep in mind, and this is something that Scott Sanford reminded me of here, that they are competing technologies. If the plate cooler does a great job of removing the heat, then there's less heat available for preheating. And from what he indicated to me, that with on Wisconsin farms that are in the range of 100 head, that maybe one of the options viable and then you have to maybe get over 150 to 200 head before both options become viable, both the plate cooler and preheating. So again, something to be aware of in more of the practical application of some of this information. So there's the end, and maybe it is. Maybe it's an opportunity or a beginning, and I guess with that, I'd welcome any questions or comments.
Does anybody have any questions for Dan?
Dan, this is Brian Holmes. One of the things that I observed in many farms is that the air-cooled the air-cooled condenser in many farms is located inside of the utility room or the milk house. And it maybe has an open vent to the outside, but there's a separation distance between the two, and so when that thing is running, sometimes the temperature in the milk house or the utility room is really high because the thing is venting the heat to the room rather than to the outside. And it seems like a relatively inexpensive piece of ductwork to make sure that that's connected directly to the outside to cause the waste heat to be directed outside would be much more efficient use, because otherwise it's sitting there circulating that heated air and it keeps getting hotter and hotter, and the efficiency of the unit keeps going down and down in the process.
Well, I think that's a correct observation. I've seen that as well, and I think some of it, these older farms, they've evolved and they've added equipment, and it's like they kind of know that they need to do that, but they've got too many other things on their list to deal with it. And yeah, but it's a common sense factor that that should be considered. It should certainly make sense.
Dan, this is Scott Sanford. Another thing kind of following that same line is that we did a study a few years ago on cleaning the units because they get dirty and caked up even if they're inside. And cleaning those, we found a 3 to 5% reduction in energy use just by cleaning them. It takes about a half hour, and so that's a pretty good payback. A farmer can usually do it himself. It requires you get a evaporator condenser cleaner fluid. Those condensing units have aluminum fins and copper tubes, and they're press fit. So if we get any corrosion between those, we don't get as good a heat transfer. So using their special cleaner versus something you might have around is a better deal. But there are some rules. You know, you got electricity there, and you need to spray some water on it. So you got to make sure the electric is shut off. But pretty good energy savings for once or twice a year cleaning.
Yeah, I think in many cases I've seen where the farmers are aware of those issues. I've seen that especially like with ventilation fans. It's not unusual to see ventilation fans that are fairly dirty, and my understanding that there's a significant drop in their energy efficiency if they aren't kept clean. But there again, the farmer will point that out as we're walking around their operation. But again, he's got other things on his list that he's dealing with, but again, it doesn't hurt to remind them of that and let them know that that's in the numbers. I think, as I mentioned, the whole thing about the audits, I think, is just giving them more or less a checklist, and based on that list, it's a reminder of things that need to be done. We run into situations where the farm has asked for the audit, but I think they want as much a pat on the back that they've done a good job, that they've implemented some of these things, and they just want it reinforced that, in fact, they're moving in the right direction, and that investment was worth it. So I think it is. It's as much a knowledge tool or educational tool as well as actually something that's going to be implemented.
Anybody else have any questions? Oh, okay.
Brian Holmes again. Dan, when you use your MSU energy calculators, do they take into account the interaction between the pieces of equipment to look at the effective payback? I was thinking about your situation with the tankless water heater that had a 9-year payback, And yet if you combine that with a waste heat water heater, that payback is going to go way up in time. And so maybe a decision to go with a tankless unit at that point may not be very economical if you're also combining it with the other.
Well, the calculation itself doesn't do that, but you can. I think you can quantify those. I've seen that with some greenhouse audits I've done where I'm looking at different combinations of either unit heaters or hot water heating combined with energy curtains, and the scenarios that we're looking at there, yeah, you can I guess come up with numbers, if you will, that says if you do the whole package, here's what your return is.
Any other questions?
Any comments on the variable frequency drives about what size you need before that they are somewhat useful?
Well, my understanding, there is a rule of thumb for the say the amount of the number of milking units the CFM needed in order to establish the I guess the horsepower, if you will, for the for the motors, and then the variable frequency drive has to be related to that. So I don't specifically understand the those values, but I guess I'm relying on the milk suppliers and the equipment suppliers to match the equipment with the product. I'm not doing that. I'm not making that specific recommendation when I'm doing an energy audit.
Vance, are you referring to vacuum pumps or milk pumps?
I was referring to the vacuum pumps, but we have a variable frequency drive both on the milk pump and on the vacuum pump. But it was particularly on the vacuum pump because Scott, you and I have talked about that sometimes it might actually be more energy efficient just to change the pulleying system rather than taking a look at a variable frequency drive. And having had a variable frequency drive burn out after 2 years, and the warranty was just out. It's a little more than slightly frustrating.
Typically, what I've been recommending, if you look at the economics of what it costs you versus the capital cost versus the energy savings, you've got to milk about 6 to 8 hours a day, or the vacuum pump needs to run about 6 to 8 hours a day for it to be a 4 to 5 year payback. That's a rough rule of thumb. On the variable speed milk pumps, the advantage there is you're trying to make the pre-cooler more effective. And what I found is if you put a variable speed drive in, you'll get 15 to 20 degrees of additional cooling from that pre-cooler up to a maximum of 2 to 4 degrees above the well water temperature. So that's kind of a rough rule of thumb.
Right. Scott, do you make any heroic assumptions that the vacuum pump might last longer, or are you saying that the life might be shortened because it goes up and down in speed rather than running at a constant?
Well, if it's hunting a lot, then it's not tuned correctly. They should run fairly constant except for when you're attaching the units. And when I say fairly constant, it'll roll a little bit, but not big shifts. But when you go put a unit on, it's going to increase in speed, of course, because you're consuming more air. But sometimes they overcompensate, and basically they have to be dampened, and that can be done through the settings on the controller itself. So that's something to get a hold of your supplier to work with you on that.
Right.
Any other questions? Well, hearing none, I'll be sending out a post-evaluation. I guess I had some problems with the pre-evaluation. There was an end date, and I didn't have it set right, so it said it expired. So I apologize for that. We'll try again next time. But I'm going to send it out a post-evaluation so you can see how how much you learned on this and how we can make it better. So I appreciate it. If you do have any additional questions, you could, Dan, you didn't have your email on this, did you?
I don't believe I included it on there. No, I did not.
What you can do is you can email me, and then I can route the questions to Dan so we can answer them for you if you have any additional questions.
I would certainly welcome that, and yeah, any feedback. It's been an interesting process. I'm impressed with the resourcefulness of the farm operations, and it's just been a real interesting experience for me these last couple of years. So, interesting stuff. All
right. Well, I appreciate your taking the time to do this, Dan, and Al Go for setting this up, and we'll call it a day. And just a reminder, next week we have 2 sessions on energy conservation for greenhouses. Other than that, we'll call it a day and hope everybody a good day. Thank you.
Thank you.